All right, so our next speaker is a second keynote for today. Dave Meyer this morning was the first one, intended to really be especially thought-provoking and give a bigger picture perspective on the world we're living in technology-wise. So for that, I'd like to introduce Len Bosack, who is, he worked at AT&T Bell Labs back when those were part of the same company, digital equipment at Stanford, and then was one of the co-founders of Cisco Systems, which I'm sure is familiar to everyone here. So Len is going to talk a bit about big picture technology, where we've been, where we're going, and I'd like to welcome Len Bosack.
Good afternoon, everyone. I hope to be able to both inform and entertain you just enough to have you overcome the what's politely called postprandial lull. No one's asleep yet. Okay, so we're okay so far. What we're going to do, this is the world's simplest slide deck. There's not a lot of apparent stuff here. You're not going to get a lot of cartoons, no dangling, jumping men, nothing of the sort. Just a few points here and there that I can arbitrarily expand. I greatly appreciate the gentleman today who talked about complexity. It's part of a rant I now no longer have to give you, since while he came at it from a different point of view, it's something that you do need to think about, and I'm going to talk about that in various ways. So here's the outline, and I can almost leave this slide up. What I hope to do is to talk for about half an hour, and then to open things up for people to ask. You can ask me anything. I may not know the answer, but I'm happy to talk about things I do know. First off, I've been working in the area of optical transmission now for actually quite a while. Since so many years ago, I was involved with a project to build a 40 gigahertz radio network all around the United States. This involved making 20,000 miles of circular waveguide. Well, fortunately, the losses in fiber came down from 70 dB a kilometer to in the tens, and people said, you know, this is going to be a lot easier. 20,000 miles of pressurized pipe run down the middle of the interstate is not easy, especially as this was the late 60s, and if you're at all familiar with what microwave technology or millimeter wave technology around 40 gigahertz takes, this was a big leap forward. Fiber was better. I'm glad we eventually figured out how. So, with that little bit of preface, we have a lot of dark fiber available in most markets and in most routes that are important. In some cases, it's not commercially accessible, and I'm not going to talk much about that, but it is what it is. Some people are there ahead of you and may not choose to share. But in particularly important areas, people are willing to take the time and difficulty to actually dig the dirt and put some more in. That certainly happens, or has happened, on the New York to Chicago run, which is commercially quite important. So the dark fiber is there. It's a bit of raw material. Now, I hope by now, remember the marketing of fiber in the bright, bright future? Does everybody remember being told that fiber had infinite bandwidth? Anybody believe that today? Oh, somebody put up their hand as a joke. All right, sorry. Every real thing, of course, has a limit for how much power you can apply before it melts, and whether there's any noise left when you listen to nothing. And in optical fiber's case, there are limits in both cases. So nonlinearities at the high power end and noise at the low end. We've done an amazing job of making things better and better. And so now at least the line amplifiers my company makes, are approaching what's likely to be feasible, certainly in terms of noise, and are much better in linearity than what had come before. The reason the linearity matters is I hope everyone now understands from the 40 gigabit experiments that people tried in the early 2000s that making the symbol rate on your line go up is not a winner. People who tried the OC768 world, I don't really know of any vendor or any user who was entirely satisfied with that experience. And there's a fundamental reason why. If you could cope at 10 gigabits per second, at 40 gigabits per second, blinking the light on and off is 16 times more dispersion sensitive. Dispersion sensitivity runs approximately as the square of the symbol rate, and that's what you were trying to do. Very hard. As the symbols became shorter and shorter, you also discovered that there's a little bit of leakage from one polarization mode to another. Won't go into the physical details of why, but it's again that nonlinearity business. It's not perfect. So, making the symbol rate go up dramatically is not on offer. It gets too hard to do anything with your medium. And yes, we have wonderful things we can do with enough matrix multiplies and digitally implemented filters. So now you find that even a single trans-Pacific fiber link without any effort at dispersion compensation can be computed out. That's not bad, huh? That's a pretty good result. But it takes power. And that's a problem. And you're going to come back to this again and again. So one of the things that we need to keep doing is to limit our ambition to what is technologically feasible and physically plausible. Okay, let's look at 100 gig as an example. The 100 gig coherent is not, in my view, a particularly ambitious effort. It uses both polarizations, that's good. Everyone who's had Polaroid sunglasses know that light comes in more than one. A very modest improvement in the use of the Fourier transform signal space available. In other words, we now have 1 bit of in phase, 1 bit of quadrature. Well, that's twice as good as not using the other phase, and 2 polarizations is twice as good as only using 1. So we've helped ourselves here, going from 100 gigabits down to sort of 25. Okay, that hurts a little more than, it's 4 times or 5 times more dispersion sensitive than 10 gig, but you might be able to cope with that, especially given that you're now going to try and compute your way out of this box. And we were able to do that, but at a price and power that a number of people found surprising. Getting to do better is going to require us to not raise the symbol rate and to do something that would have been understood by Claude Shannon, or Harry Nyquist for that matter. And we have to put more bits per symbol, okay? Our next stop, logically, is probably going to be 16 QAM. You'll get your 400 gig out of that. That's a nice number. That's 2 bits per I, 2 bits per Q. That's an improvement. And you could certainly do 200 gig. And whether you want to go to 64 QAM to do 400 gig, okay, I'm happy to listen. I think you should, but that's me. I think increasing the power spectral density is an important thing to do. Some people might disagree. There's always more than one way to do a thing. Notice that you might have heard the argument going on about, well, what's this quadrature AM business? We should immediately go to this much better scheme called orthogonal frequency division multiplexing, and we should just skip the whole thing. Well, it turns out that if you look at the problems you run across, by the time you get to 256 QAM, and various simple forms of OFDM, they're about the same. So the two solutions eventually converge, and what you want to call it at that point, you're arguing about implementation. So people understand, if you haven't heard the executive summary, OFDM is essentially Fourier transform demodulated. What you do is you sample a given period, take the discrete Fourier transform, and every point that you get has a magnitude and a phase. Well, guess what? You can treat that as a quadrature data carrier. This is how the original 9600 baud modems worked. It's an idea that's been around a long time. But in the age when the 9600 baud modems first came out, it was a bit of a feat to do the FFT in a box that didn't melt your hand when you plugged it in. Now it's less of a feat, and here we go. So there's a bit of the future of optical transmission in my view. I think we're going to get to a terabit per carrier in a reasonable period of time. I am not at all convinced that the cost per bit per second is going to fall very fast. There's some bad news for you, but I hope that's not a big shock either, because with 100 gig, you could probably turn up a 100 gig link. What do you think? 3 years ago? You know, people had, hero experiments and things of that sort that were running, but if you actually wanted to make a business case to put it in revenue service, it wasn't there. You were better off with a wide roller skate with more 10 gig links. So here we are. We're going to do better. Right now, if anybody thinks that they can take 100 gig equipment from two different vendors and hook them up to the same piece of fiber and have them talk, anybody here believe that that's possible? I mean, usefully. You can get some results, but you're not going to likely get the full. There are some things about the way 100 gig was done, in particular hints about constellation steering to make the thing wake up faster, that won't work across vendors as far as I am aware. Perhaps I'm misinformed, but there you go. I'm sure that the chipsets from both Sienna, that is the Vickers of Nortel, and Alcatel-Lucent could be microcoded to deal with the NEL hints, but I don't know whether that has been done. So if you just go and buy something, just right now, it's much easier on you if you put the same gear at both ends. At 400 gig, I have a small bit of optimism. Part of that is that the first folks who want to get there are our brothers at the IEEE. Now, sometimes all these committee efforts are criticized for producing large documents and taking too long. But in spirit, the IEEE does believe that if you read their document, you ought to be able to make a working example. I'm not sure every other organization in the standards world believes that as strongly as the folks at the IEEE. So I have some hope that you will, at least in some mode, be able to take different vendors' 400 gig equipment and have them talk successfully, and without a great diminution of capability. We'll see whether I'm right. That brings us to one of the other things about the optical world that we face. Okay, quick now, I've got this 400 gig system, here it is. What you going to hook it to? Well, nothing right now, because there is no user interface of any device at 400 gig that, I know you could build one, I'm certainly capable of building one, but no one really is selling a product that does that. Okay, what do you want to do? Can we take the 100 gig scheme and have 40 10 gig channels? You could. I'm not sure you'd want to own that for very many of these, but you could do it. So looking forward, people are trying to make the number of wires not go up so horribly. Because if you got to a terabit, do you really want 100 of them? That's probably beyond the elastic limit of people's ability to lay out boards and build microwave-capable connectors. The discussion going on right now is how to get more down a single pin. And if you look, it's great fun. One of the wonderful things, again, about the IEEE is if you look at their slideware for the committee meetings, you can see what people are thinking about. And these ideas range, generically, the idea is that you're going to get what amounts to a modem per pin, and it's going to be a more complex signaling system than just binary. The first one that people are talking about is a thing called PAM4, which uses 4 levels, all the way to, I was talking to a fellow at Hitachi Research, and they have actually built a small example of what amounts to, think of it as DSL at microwave frequencies. And no, it wasn't a lot of Fourier transform points and all the rest, but it did get an impressive amount of data down a small set of pins. Don't ask the question yet of how much power this is going to take, because just today you don't like the answer. The belief is that no one is going to implement a 400 gig anything with an IC geometry larger than 28 nanometers. You won't like the power. You're probably not willing to pay to cool it and all those other things. We'll talk about a little indirectly again. So there's where I think we're going to go. We will have to improve the data density somehow, because we are able technically to get into the terabit range. Whether we can get to 2 terabits or 4 terabits or 10 terabits, that part isn't so clear to me, but we'll see. It's not clearly ruled out. I know how to get to a terabit. I wouldn't be willing to make the claim today that I know for sure how to get to 10 terabits. Solving the user interface issue is interesting because, again, if I get to a terabit and I've used every pin in the universe and exhausted my ability to route microwave signals around a board, how am I going to get to 4 terabits? There's got to be a little more give in the system than we have today. So my prediction is there will be this modem per pin approach. And whether they call it that, well, it's one way to view it. Okay. If you want me to come back to this, for optical stuff, I can talk about its history and its future almost indefinitely, and I know that I will be putting people to sleep if I go into too much more detail. So let's avoid that one. And let's talk about my second point. Why were some of the fundamental decisions made about how the protocols you recognize as IP made? There's a much more general view of internets that Vince Cerf claimed I was the only person ever to believe, but I guess you should know. So if you have routers that agree on how to interpret some addresses, when those routers manipulate encapsulation functions, and all of these have more formal mathematical definitions, but they're about what you think the words mean. That's how you get an internet. Notice how little that told you. And so part of the challenge of producing the internet protocols was how little could you say about the network and how it behaves and still have useful communication occur. Okay? So the current networks that you see today are simple examples of the internet form that I described. And that all includes NATs and includes devices that no one's built on a commercial basis. And it includes potentially arbitrary numbers of non-interchangeable or non-interroutable protocols. But leaving those bits aside. The internet protocols that we have today make the assumption that the network is time varying, is unreliable, and that you have to get results despite that. So you get the Ds. We promise you that we will delay in variable form your packets. We will disorder them unpredictably, including repeating them, by the way. We will drop some of them, and the worst of all, we will even damage a few of them. So there are the Ds of the internet. This is what the network is expected to do. Not what most people think of when they think of communication. But despite that, it turns out you can produce useful results. People start to forget these things in time. And so let's talk for a moment. I suppose, actually, I should be scrolling through these things. All right, what are we doing here? Look, I've got this stuff in my head for decades. It's hard to remember. At some point, you don't know what you know, right? So I only need a bullet point to go off for a long time. All right. Well, you might as well admit what you are. All right. Okay. When I hear about this heartbleed bug, sort of think for a minute. Well, that's too bad. Anyone can write everyone who has written a program of any complexity has written bugs. Anybody here want to say they've never written a bug? It's okay. We're over with that one too. But what bothered me about it was a bug that resulted in a security vulnerability in a feature that should have never been implemented. What good? Okay, well, there's at least part of the choir here. What good does it do your user to know when they're not using it that the network has vanished? Now, it's not that there's no cases where a certain amount of null transaction work or other things might be useful, but just in general, there's no benefit to know that something that you don't, to know the answer to a question you didn't mean to ask. I think I got that right. If the network vanished while you were, so here you are, you've gone to look at your your checking account statement, you've got it up on the screen and now you're looking at it. You're trying to figure out, well, what the heck was that? Did I really do that? It takes you a few minutes. So, while that's happening, none of the paths, say beyond a first hop or two, that you used to do that transaction are there anymore. They've changed. Why do you care? Even if the server that you used is inaccessible at that instant, it's not your problem. There's no advantage to your knowing that it's not there. So it wasn't in the early days that we didn't know about keep alives. It's just that because we knew the network was going to be time varying, they were explicitly disallowed. You have to go read some 2-digit RFC to discover this, but we actually did write it down as well. So, careful what you implement when you're looking at these features. They have to be thought with a little more with a more, respectful point of view of the problem. Be sure that you're solving a problem that's worth solving. This principle comes again with the routers. I hear various people tell me that they're not terribly happy with the power and the cost and the size of the routers that they're having to put in. By the way, I've heard this before. And the answer to that question is, well, is the vendor giving you what you asked for? And largely the answer is yes. So, part of the issue, for example, now here's something that used to cost a lot of money but now doesn't. gigabytes and gigabytes of buffer are a horrid idea. You need as much buffer as it takes to make a stable statistical measurement, to run your statistical congestion control protocol, and you should have no more. More buffer than that, as a network gets larger, is a disaster. It starts to cause these wave reactions that are just maddening when they happen. Don't do it. 2 milliseconds worth of buffer, if you've got a good, if your statistical control algorithm is working well, I don't see how you need more than 2 milliseconds worth of buffer to do it. Okay, that's my view. Okay, infinitely long access lists in the core. Do you really need your 2,000 term access list on your input and output interfaces on every one of your core routers? Could you just say no? All right, well, part of what you're getting is what you've asked for. And when you look at what it takes to build a router, it takes longer, right? It's still not easy. If you want to build a fairly straightforward router built out of pretty much commodity computer components, there's any number of folks that you can basically take a PC, put some extra interfaces in it, run Viato or run some Linux package. You build by yesterday's standards an okay router. It's not too bad. But you're not going to get humdy-ho terabits through it. So if you need to build a router that is near the state of the art, you have to start a long time ago, and I'm sorry for those who wish this not to be true, you probably still need to need to build your own ASICs. I understand that people wish that not to be true, but I just don't see a way around it when you get to the highest levels of performance that people want. But if you could take out all these edge features, you might very well be able to get the power and the cost down. You can certainly get the power down. Well, there you have it. I assume that the talk this morning gave, there's a lot of ways to come at this one, but these couple examples tell you that you need to review what you're asking for in your RFQs and RFPs as to whether what you are asking for is good if you are given what you asked for. As a router vendor, you get these various things coming in, and you know that years from now is when you're going to get your next product out. So you're steering a supertanker. You don't get to change your mind very often. And so what do? You tend to build for a superset of things that come in the RFQs. Well, I mean, the engineering people say, oh, yeah, that's going to take a lot of time and money and power, and they say, all right, well, 3 bags full, here you are. So the final bullet is, do be careful what you ask for. If you get it, you might not actually like it. Okay, let's go on to another one before we turn things over to questions. And if people run out of questions, I can continue to rant at you for more time. I suspect you'll have other things to talk about. Okay, years and years and years ago, I worked for this thing called the Bell system. And whatever you thought of the Bell system, it actually had some people who did think carefully about how to build something of that size, because no one else was building a transmission and switching system of that scale. And we'd understood, for example, at the level of how reliable does a relay contact have to be in order to give you a service goal. And this was a good thought to have. They separated transmission from switching for one overriding reason, which was they wanted to be able to make progress in one side without changing the other. And at that time, switching was progressing much more rapidly. I was there in the late 60s. Transmission was progressing, but switching was making a whole lot more progress. This was the age of digital everything. Computers were coming about. The great optimism of the number one ESS, remember 2 hours downtime in 40 years? Oh, people don't know that story. Can't tell it to you, but the reliability spec was 2 hours in 40 years of downtime. Not bad, huh? How's that compared to your SLA? You can't say that we lacked ambition. It didn't work out that way, needless to say. Transmission was advancing, but nowhere near as fast, and they wanted to be able to have independent advancements in microwave transmission, cable transmission, eventually fiber optic transmission, thus no 40 gigahertz waveguide. It isn't so clear to me that we're not better served today from being sure we maintain that. Fiber on long-haul routes only runs where it runs. Even if some guy digs it up with a backhoe, the other fiber routes didn't change where they were. It's a very slow change in those aspects of the network. You don't need a lot of sophistication to shovel your bits down at the optical level. And it would be good if you refrained from asking for it. Oh, the buzz nowadays is you've got, Nick McCune's software-defined networking, which sort of, jams tables into switches, and some people might like to use MPLS at the optical layer, and that there's room for more than one solution in the world, and these things have certain merit, but do be sure that it's actually worth doing, given the rate at which people can change where their fiber goes. You may very well be better suited with something that's very simple. I mean, my view is that you should have a simple solution to a simple problem. And because the fiber isn't going to move anytime this week, you don't need to do anything on a scale shorter than that. So that's one view of the problem. And if you keep it simple, you can keep your costs down and permit the advances in modulation to be what drives the improvements in transmission. And so the final point is the bottom line for a number of these things. Be careful what you ask for, because if you get it, you might not actually like it. Simple is indeed better most of the time. William of Ockham had the point about Occam's razor. The simple solution is usually the right one. I think we need to be somewhat respectful of that. Sometimes because we can build complicated systems, we think we should build complicated systems. Maybe not. All right, I see that we're getting on towards half the time is gone, and I hopefully have not irritated too many of you, but inspired some thoughts. And let's now ask for questions, comments, whatever you want to talk about. Here we are. Go right ahead.
Hey, my name's Kevin. I'm from eBay. I wanted to ask about, you talked about doing the modem on a wire sort of thing inside. How do you think the photonics will impact that? We're hearing a lot, at least I am, about sort of the silicon photonics stuff that's coming out as sort of the new interconnect within a box.
Okay, I didn't mention this aspect of it. In trying to raise the amount of data you can get out of a single, let's call it port on an integrated system, one of the alternatives to electricity is light. And I have great hope that this in time is going to be the real solution when we get closer to a terabit. There have been for, let's see, Intel I think reported some modest success 10 years ago, something on that order, maybe a little longer. And there's a number of quantum challenges and process problems, but it's getting to the point that we can build a reasonable number of modulatable light sources, certainly at 10 or 20 gigabits per second on a chip. And there are problems about, imagine the problem of aligning all those light sources with whatever you use to move them across. One of the really neat systems that I've seen essentially took the chips and mounted them on a substrate right next to each other. So basically, it was free space. Everyone remember free space laser transmission? It's the only problem is when there's fog. Well, no fog inside the chip. And it's a sound solution. It will eventually have a place. I just don't know when. So that's my view on that one. Yes, sir.
Hi, Phil Rosenthal from IS Prime. So I don't know anything about the electronic side of getting the lots of bits down an interface, but it seems to me like there's a lot of unnecessary complexity that's being done on trying to get these really, really fast optical channels. And it might be an easier solution if perhaps you would say, well, let's start building our WDM prisms to have, say, 200 gigahertz wide channels or something like that, and then within that, if you want to have, whatever link speed you want to have, 100 gigabit link speed, put that at a 25 gigahertz spacing, 10 waves of that within that, and if you do that, then all of your issues of dispersion, etc., maybe don't matter. And one other thing, so you can respond to both. With buffering, there is a big issue that's happening nowadays where you have a bunch of really high bandwidth CDNs, like Netflix as an example. They have all of their stuff connected by multiple 10 gig ports, sending out bits to maybe somebody that's on a 1 megabit DSL line somewhere. So we have all these incredibly stupid TCP stacks that will basically say, okay, you have a long fat pipe, and the user requires a burst of requires 100 packets in flight. So rather than sending one packet per per millisecond, space it out over 100 milliseconds, we're just going to send 100 packets right now, and we're going to wait 100 milliseconds, and we're going to send another 100 packets, which causes that needs to be buffered somewhere. And if you want to reduce the requirements of buffering, and I agree you should, somebody needs to explain to the people who are writing these TCP stacks that they need to start spacing out where they send these packets, which currently nobody is doing.
Let's start with the second point first. You're right about the ultimate solution, which is to spread the traffic over time, which is all the user can get anyway. I have another footnote on this that I'll come back to after we talk about the first point. One way to explain that to the TCP writers is to throw their traffic away. Okay? If it didn't work to take those 100 packets and generate incredible variation in delay for some other user, they would indeed, actually if their TCP is well regulated, thank you Van Jacobson, they would indeed detect that they can't put that much data into the pipe no matter what the far guy's window was. So they would indeed think of it as congestion. That's okay. So I believe the explanation there is if the people who have responsibility for the various TCPs are not able or willing to deal with a more modest client rate, you explain it by throwing it away, and they will adapt. So that is my answer there, that it needs to be explained perhaps more dramatically than it is currently. The buffering, once again, is the problem, not the solution.
I agree. It is actually, it's a very appropriate answer. By breaking things, you force them to fix it.
Yeah, if it didn't work, they'd do something else, if something else did work. Now, back to the first question about what do you do, why is there this endless quest for greater bits per hertz, basically, for spectral density? it does come down to the question of aberration being sensitive to the square of symbol rate. So as your total bit per second goes up, you need to keep the symbol rate capped. And I don't know whether 25 or 28 gigasymbols a second is the practical maximum. We fiddled around with some things that produce a tremendously robust 10 gig with, gigahertz scale symbol rates, which means that dispersion is very far away from being a consideration, as well as certain other phenomena. So a suggestion that we reorganize our long-haul system into simply a collection of super channels and let the users sub-multiplex them into whatever they want, that's a perfectly valid system design. But in terms of economy and power, in time, you may find yourself better off with the more spectrally efficient solutions because the symbol rates remain low while the data rates go up. Part of this is also an exercise in the possible. We have now reduced transmission to a problem in computation. And one of the things that we do know that the folks with the miracle printing press can do is give us more transistors smaller and faster. So you are, in Bertrand Russell's summary, in league with the future by reducing it to computation. So I know that line will work. Whether the other approaches work out well, I'm interested to see whether people try them.
Thank you.
Quite welcome. Yes, sir, on the left, my left.
Colin McIntosh, SIG. I know that you mentioned that people should be careful about the features that they request from vendors, but as I think people will continue to ask for features that make their lives easier, how do you think vendors can combat unnecessary feature bloat in a world where if they don't build it, someone else will?
Well, that's an interesting market question, which is partly education, and there's some value there. But if people ask for something and it ends up being big and power consumptive, and someone builds a simple thing and the complicated hot one sells, the market says that they were right to build the complicated hot one. So you have to vote with your checkbook. If you find a simple solution that in a simpler or more restrained system design will solve your problem, you ought to vote by buying it. That's how you do it, because you have control. You have the checkbook, and in a more or less free economy, you do control what you get.
Thank you.
Yes, sir.
Nico Smoot, TierPoint, but wearing my 6 hat. I think I heard you comment that 100 gig between separate vendors, good luck making it work. As an exchange point operator looking to deploy 100 gig, I understand that there's other exchanges running 100 gig. Could you elaborate on those comments about?
Perhaps I didn't say that very well. What I was talking about is the long-haul coherent modulation. The user side, where you have various switches with 100 gig E, for example, with a certain amount of testing and care, that should interoperate just fine. I don't think there's a practical problem in making that go. That's the area that mostly we have the least trouble with. Again, I won't give you the footnote on that one, but that's something that appears workable. I mean, for heaven's sakes, you can go out to Spirent or Ixia, and you can buy a tester that will exercise those links in pretty good, to a pretty good depth. Not every possible case, not every corner case, but generally speaking, if either of those vendors' test gear says that the port works, it probably does work, and you probably will be able to interoperate. So as an exchange point vendor, I don't think you're in trouble at all. I think that the place that we're in trouble is on long-haul transmission, that if you tried to put Sienna gear at one end and Alcatel-Lucent gear at the other end and think that you were going to have as good a conversation as you would from Siena to Siena or Alcalu to Alcalu, I don't think that would happen. Or if you take something made by NEL and try to talk to Siena, they may very well have enough compatibility modes that something could be made to work, but I don't think you'll get as good as an experience right now. Whereas at 400 gig, I think we'll fix it.
I don't think I'd be comfortable even expecting that at 10 gig, so.
Oh, well, at 10 gig it didn't used to work either, but now it's a lot better at 10 gig. If you're careful about the component selection that you have, I think we're able to make different vendors 10 gig talk to each other, but that was not always true. Yes, sir.
Sinatra, ESNet. I think if you ask a lot of people in the room, is the Shannon limit out there? Is there a Shannon limit? They'll all say yes. My reading of your talk on the optical side is that you're cautiously optimistic that we still have a ways to go. Mm-hmm. I don't know if that's I don't know if I interpreted that right.
That's fair.
Do you think that we are increasingly making our living off of using the network for more and more things that we would otherwise use physical things? We don't go out to a store and rent videos anymore. We don't go out to go out to a store and buy things anymore for the most part. So we are acting as if we sort of have this assumption that the network is going to keep going up and to the right. Or to what extent are we operating on that assumption, and to what extent is that a problematic assumption, and what happens when we bump our head? Just interested in your thoughts on that.
Well, I think we are going to go up to the right for a while. I'm pretty sure that we've got another factor of 10 in sight beyond 100 gig, and that'll happen maybe a little slower than some people like, and it might be a little more expensive, but I think it will happen. How far we can readily go beyond that? Well, we're not hitting real theoretical limits. As I say, we're now probably within a factor of 2 in linear of amp performance as far as noise goes, and a factor of 4 or 6 in the high-end power linearity constraints. So there is more dynamic range to be had in the long haul with those technological improvements. But to say that we can go on indefinitely, perhaps not, because now one of the principal noise mechanisms, our amplifiers are hybrid Raman EDFA amplifiers, and not to go too deeply into the physics, but it's weird. This result is absolutely weird, and it might amuse a number of people. The Raman amplification process, Raman inelastic scattering, is noise-free. It generates no noise of its own. Yet when you hook a fiber to a Raman amplifier, noise does come out. You don't get zero power out the other end. And the apparent reason is truly bizarre. And the answer is that space is unstable. What you are seeing is the result of imperfect cancellation of the vacuum fluctuation. Anybody ever have something that weird in their garage? Okay then. So I do think we are going to go up and to the right for a while. And again, you can argue about cost and all the rest, but I think what will happen is it'll go up to the right and then ooze out like everything else. It's not going to fall over dead in a day, and it's not that it won't be possible to progress. And do remember, we actually have quite a lot of fiber in the ground, and if it became economically viable, why wouldn't you run the trenching machine again? Well, I think we would. So, but that usually only gives you a factor of 2 to 4 before you start to feel like you've Swiss cheesed the earth. So it's, that runs out too. Everything runs out. I suppose part of that is the common sense observation that nothing goes forever. So yeah, I'm optimistic. I actually am optimistic. Okay. We have a few more minutes. Okay, good. All right, here comes another. It's better to hear what's on your minds.
Hey, Kevin again from eBay. I wanted to see if I could get a little more context on the too much buffer is bad. Is that in a long haul internet backbone? Is that different in a data center in your opinion? I've heard Andy Beckelsheim, among others, promote large buffers in data center spaces. So I'm curious to your perspective on that.
Well, and he sells switches, you know, and it is data centers, and you know, by running enough DRAMs in parallel, you can make all the buffer in the world. So it's a solution that's available to him. When you have a small number of streams, the analysis that said that you should have as much buffer as your essentially round trip time could hold at maximum rate, that's a single user analysis or a single stream analysis. And it has a limited superposition argument, but it is, when notice I said superposition, which a number of you should, your noses should twitch because, oh, what do you mean? He said linear, right? Buffer and queuing systems aren't linear. Well, at least not in the large, they're not linear. So there are a couple ways to come at the problem. When you have a large number of flows that are going to and from stations that have differing delays, I can state pretty authoritatively that large amounts of buffers are going to be bad for you, especially in the case where a fellow was saying that, you know, here comes a content distribution network with a fast interface talking to one particular client with a slow interface. That's a problem that we've had for a long time. The numbers sure have changed, but the problem is no different. And there, not having a terribly large amount of buffer helps remind people that they should be paying attention to flow control issues. One of the great contributions that people have largely ignored out of the ISO work was a thing that used to be called the DEC bit, which lives on in the IP world as the congestion experience bit. If people were to actually set it and correctly obey it, you would find a tremendous improvement in the stability of your network, because it helps those who are more aware of congestion rapidly adapt to actual conditions. They don't actually have to lose data before they start to adapt. Right now, with Van's excellent work, you actually still do have to lose data before you adapt effectively. So one solution to that particular problem is do use and obey the congestion experience stuff. Now let's go turn the problem around. In a data center, let's see, what are you going, a couple hundred meters typically? So there's not a big delay in terms of the speed of light. You have a couple hops through some switch complexes, and you have likely engineered your backbone links to be faster than your tributary links. If that's always true, whether there's a lot of buffer or not is dramatically less important, because there shouldn't be a big buildup. So the presence of the buffer isn't the problem, it's just using it. Go ahead, put all the RAM you want in the world, just don't use it. It's bad for you. It produces these surges that you know, one guy gets in the way of another too much. So, you know, I don't know, why Andy's come to the conclusion he's come to, but in a data center, if it's engineered with an increase and then decrease in link speeds, you will very rarely find yourself in trouble. So that's my view on that. Yes, sir.
Scott White, Google. So I agree completely with your views on the buffer bloat stuff. But TCP has another fundamental issue, which is when we talk about fairness or TCP friendly, it's really window fair. It's not rate fair, right? And which is what I think, the earlier discussion about we should just drop packets, right? Because really the only way to enforce rate fair right now is on the routers. So what's your views on that? Is that something that we should try and address directly with TCP?
I've experimented over the years with protocols that, okay, everyone knows what Van Jacobs' work was done with in a wonderful environment. He had a 10 meg Ethernet going to a router that went to an IMP that had a 50 kilobit connection to its adjacent IMP, and then back, so from Berkeley to the other site that he was going to. He came up with a very clever scheme to figure out how to rate meter, and that was to start with 1, wait around trip time, 2, and so on. Everybody knows the scheme. And when you dropped something, you cut back by a multiplicative factor, and over time you went up by an additive factor. And if you were willing to tolerate a few losses in there, and your timeouts were correctly adapting to the round trip time, you did pretty well about figuring out how to rate meter yourself. But it wasn't a real rate meter. It was a quantity outstanding meter that turned into a rate meter because of the way the ACK flows work. You can do very, very well if you know what the slowest link speed in your path is. If it's clear that there's only a megabit of available bandwidth, why are you ever going to send an average higher than that? That's wrong. But right now, the network doesn't generally give you enough information to know that. I mean, our brothers back at Netflix might have servers with 40 gig links running around their data center, and gee, it looked good to them. So why shouldn't they simply blurt out whatever the window size is worth of packets and move on? Well, the answer, of course, is that the truth of it is that they should only be sending things at a megabit per second, because it can never be better than that. Now, many years ago, I experimented with routing protocols that could tell you path properties. And it was a good idea then, and it's still a good idea. If there was a way for you to ask the network, okay, for this destination IP address, just right here, right now, how fast can I get there? And it would tell you essentially the free link bandwidth between you and them, the minimum over the entire path. Well, we probably couldn't do that consistently and perfectly over the whole internet, but we could do better. And if you had that, you want to have your TCP meter data out at just that rate. It doesn't have to be accurate. It just has to do sort of a nod in that direction. If it gets it within a factor of 10, it's a big improvement over what we have now. And it would probably, again, if the network itself had a reasonable amount of buffering, actually produce fewer dropped packets than almost anything else. Now, that's my thoughts on the subject. We should be rate metering, and we're not giving the end stations any help. If we gave them help, we could do better. All right, well, I think I'm going to get you on to the next talk on time.
Yeah.
I try very hard to do that, because if you start the first one after lunch, and if you're late, everybody's late the rest of the day.
No, thanks very much, Len. And our next thing is actually a break, so you can stretch your legs a little, get a coffee.
Even better.
Yeah.